today we're going to start 13.4, which is motion in space. We're going to talk about velocity and acceleration. So we're going to show how the idea of tangent and normal vector and curvature can be used in physics and study the motion of an object, including velocity and acceleration along a space curve. Okay. So suppose a particle moves through space. So imagine this is a particle moving through the space, okay? And the position vector at time t, so this is the position vector at time t, rt, okay? And for a small change in time, h, okay? Think about h is a small change in time, okay? Then after a small change in time h, then the particle is moved to here. And then we have the new position vector, r of t plus h. Now, if we think about this difference quotient, okay, r of t plus h, subtract r of t, and then divide by h, we got a vector pointing this way, okay? And this is a 1 in the blue rectangle here. This vector here approximates the direction of the particle moving along the curve. Okay, so think about it like kind of the secant, right? A secant trying to approximate the tangent, right? This one here approximates this, okay? Its magnitude measures the size of the displacement vector per unit time, okay? So this is the displacement, subtracting the two positions here, you get the displacement, and then the t here, h here is a change in time, okay? So this is it measures the size of the displacement vector per unit time, okay? This vector over here, I'm gonna label this 1, okay? That gives the average velocity over a time interval of length h, right? Kind of familiar with the two-dimensional case, right? So how do we figure out the average velocity? We use the final position, subtract the initial position, and then divide by the h, right? Divide by the change in time, the time elapsed, right? So that's now the average velocity. And we take the limit of this average velocity as h approaching the zero, and make this time interval to be smaller and smaller and approaching the zero. And that is equal to the instantaneous velocity at that time. Okay, this is not the two-dimensional case. And as you can see here, if you look at the graph, this one here, as the h here approaching the zero, then this is going to approach to r prime of t. This tangent vector over here, right there, okay, let's see, approaching to this. So the velocity at time t is actually the duality of r at time t. These two are the same thing. So I use the same color here. You can make the connection there. So the velocity at this time t is the duality of r at time t. Okay? This is the velocity. Okay? So the velocity vector is also the tangent vector and points in the direction of the tangent line. Okay. As you can see here, it points in the direction of the tangent line right there. Okay. Now the speed of the particle at time t is the magnitude of the velocity vector. How do we find speed? Speed is the magnitude of the velocity. So for magnitude, we put the absolute value there, right? And we can just figure out what's the magnitude of the velocity, and that will be the speed, okay? Speed is a scalar, okay? It's a magnitude, okay? Velocity is a vector. It has magnitude and also direction. Question? Okay. So now we can make the connection between the 3D and the 2D, okay? We can see that was appropriate. The velocity vector, okay, is equal to the vector r prime, okay? And that's equal to dsdt. This is a change of the r with respect to time, okay? That's rate of change of distance with respect to time. Rate of change of distance with respect to time, okay? So as in the case of one-dimensional motion, right? Remember when we have 110A before, what do? We do that. Acceleration is the derivative of velocity, right? And it is the second derivative of the position function, right? So this is r double prime t. Okay, very similar, right? Okay, now let's look at some example and try to understand this a little bit better. Okay, and let's do this together. Okay. So the position of I'm gonna ask someone to read that. How about Raymond? Could you read this from here to here?
The position vector of the object moving in the class is given by r of t equal to t cubed I plus t squared j. Finding its velocity, speed, and acceleration when t equal to 1 and illustrate geometry.
Okay, thank you, Raymond. So now, in order to find the velocity over here, right, we are given this is it's like a position function, right? The vector is a vector function of this the particle. Okay, so to try to find the velocity, we're given this. What do we do to find the velocity?
Take the derivative of r.
Take the derivative of this, right? So if we take the derivative of this, what do we get here?
3t squared plus 2tj.
Yes, you got it. Good. So, and how do we find the acceleration?
Take the second derivative of rt.
Right. And then we differentiate it one more time, then we get the acceleration, right? Okay, good. All right. You got it. Okay. So you just differentiate first. One time you get the velocity, differentiate one more time, you get the acceleration, right? Okay. And how do we figure out the speed? It's a magnitude, right? So we just figure out the magnitude of this. We'll take this square root of this square, 3t squared, and then plus the square of 2t. Okay, so this is the speed, okay? It is a scalar function, okay? So when t equal to 1, we try to figure out the velocity at time t equal to 1, right? So what's v1? How do we figure this out? Substitute 1 into the velocity function, right? Okay. How do you figure out a1? Putting 1 into the acceleration function, right? And then for this one here, the speed, you just substitute 1 into the speed function, right? Okay, good. Now we're going to graph it, okay? So we're going to illustrate this, graph it, okay? So actually, I graph it over here. In 3D, it looks like this, okay? This is, it only has the x and y. It's on the xy plane. Only have the I and j component, right? So it's on the xy plane, okay? And then this is a graph, okay? It's totally on the xy plane, okay? Then what happens when t equal to 1? T equal to 1 is at this point 1, 1, like that, okay? So if you're looking at the xy plane, so 1, 1 is right there. And the velocity vector at 1 will be this one over here. And how do you draw it? You will go at 1, 1, you go 3 units, 1, 2, 3, and then you go up to 1, 2, and then you draw the vector there. And for the acceleration vector at 1, you can, this is 6 and this is 2, so you go 6 in the x direction and you go up 2 in the y direction and you draw the vector. So you get the 2 vector there. Okay? Question? All right, now I'm going to let you practice on this. How about you guys practice on this or working maybe a group if you want, okay? So try to figure this out. Okay, so we get the velocity vector, okay, and then acceleration vector, we're going to what? Differentiate that one more time. So what do we get? Negative 9 cosine t minus 8 sine t, right? And then what about this? This is the speed, right? Okay, and then what do we do with
Square root.
take the square root of this, right? Then what do we get? Oh, I just set a timer. And in reverse side, this one here, this is like 81 cosine squared t plus 64 sine squared t. That's it. Okay. Then we cannot simplify this any further. Then we just leave the answer like this. Okay. Huh? You can leave. Question.
Can't you take out like?
Uh-huh.
Oh, never mind. I'm wrong.
Oh, actually, you could do something. You could do something because this one has 64 of this. What about we try to break it into 64 cosine squared t, and then adding 81 subtract 64, that would be 17, right? Is it cosine squared t? Right? Right there? Right? And then the reason for that is because this, adding this is equal to what? 64, right? So these two add together is 64. So the answer here will be square root of 17 cosine squared t plus 64, right? Okay, good. Okay, good job. Question? Okay. Now let's continue. I need to. So in general, okay, I'm gonna ask Kyle, could you read from here to here?
In general, vector integrals allow us to recover velocity when acceleration is known and position when velocity is known. Vector t, okay, I can say velocity is equal to velocity of initial time plus the integral from t naught to t of the acceleration, which is, and the position vector is equal to the position at the original time plus the integral from t naught to t of the velocity. If the force that acts on a particle is known, then the acceleration can be found from Newton's second law of motion.
Okay, very good. Okay, let's just stop here for now. So the velocity at time is equal to, think about this, if you start from this initial time t naught, right? There will be the initial velocity and then plus this integral from t naught to t of this acceleration function. Okay, this reminds you of the fundamental form of calculus, right? Because this integral is equal to this subtracting this. The integral of the rate of change is equal to the net change, right? This equal to this subtract this. This subtract that is the net change in velocity, and acceleration is the rate of change of velocity, right? So that's actually fundamental theme of calculus, okay? And similar for this one, the vector function at time t is equal to the initial vector plus this integral of the velocity function, right? Okay. So again, it's like the fundamental theme of calculus. This is the rate of change of r, okay, or r prime, right? So this is like an r prime, okay? then when you integrate this rate of change from T naught to T, it's actually equal to RT subtract RT naught. Okay, so this. Okay, so if the force acting on the particle is known, then the acceleration can be found by Newton's second law of motion. Do you guys remember what's the Newton's second law of motion? What's the first one? Yeah. Yes, the second law of motion is force equal to down here. It's a little bit, okay. And force equal to mass times what? Acceleration, right? That's the one. The second law. Okay. Okay. So you have a mass here and there's force. The force is always equal to the mass times acceleration. Okay. The force causes acceleration. If you have acceleration, there must be a force acting on it. Okay. Force equals this. Okay. F equals ma. Okay. Now let's take. We're going to talk about projectile motion. Is that how you say it?
Yes.
Yes. Motion. Okay. So I'm going to ask Julian. Could you read example 5 from here to here?
A projectile is fired with angle of elevation alpha and initial velocity v naught. Assuming that air resistance is negligible and the only external force is due to gravity, find the position vector RT of the projectile. What value of alpha maximizes the range or the horizontal distance traveled by the projectile?
Okay, very good. So a projectile, okay, fired with the angle alpha here. Okay, the initial velocity is v naught. Okay, assume that we can neglect the air resistance. Okay, and the only force acting on the object, at any moment, is just the gravity. Okay, that's the gravity. And then we try to find the position function RT. Okay, so at any given point, we try to find RT. Okay, like that. Okay, and then we also try to find out what will this angle be, so that it's going to have the maximum span, the biggest span over here, the furthest one. So if you throw a ball across, what angle should I throw it so that it goes the furthest, right? Like when you play football, right? So we do that. Okay. All right. So now you think about what angle would that be. We're going to talk about that. Okay. So we're going to set up, okay, to make things simple, we're going to set up the coordinate this way, okay? So when you throw the ball, we're going to place that position right there at the origin, okay? It's origin right there. And so, and then we have this velocity and then that projectile right there, okay? The only force, the only external force on the object is the gravity, right? Okay, and the Newton's second law say that the gravity is equal to ma, right? So that force is going to cause acceleration, right? But that acceleration over here, what will this acceleration here be? That acceleration is a gravitational acceleration, right? And it is pointing downward, right? It's pointing downward. So it is on this y direction, but since the y-axis is going up, so pointing downward, so you have to put a negative sign right here. Okay, so it's negative the gravitational acceleration. So g is 9.8 meter per second square. Then a over here will be negative g because going up is positive. Y direction is positive up, going down is negative. So that's why I have the negative sign there. And then it's on the j direction. This is I, and then this is j, right, like that. Okay. All right. So that is this. Okay. Okay. So A is equal to what? The acceleration equal to what? Negative g in the j direction, right? Negative in the j direction, okay? So since the duality of velocity is equal to acceleration, okay? So duality of velocity is acceleration. So over here we know acceleration. How can we figure out velocity? So this is the duality of velocity. If we know the duality, how do you figure out that? You integrate it, right? Find anti-duality of it, right? What's anti-duality of this? Okay, G, T, in what direction?
Y, so the J,
In the J direction, and don't forget to press a
C.
constant vector at the end, right? You got it, good job. Okay, so you got this right here, okay? Now if we plug in T equal to 0, right? We plug in T equal to 0, and we can figure out this constant vector C, okay? What does C equal to? Plug in T equal to 0, C equal to, plug in T equal to 0, this part here will be 0, so V0 equal to what? C. So basically, the velocity is always the initial velocity, right? Correspond to the initial velocity. Okay. So therefore, we can plug this back, the C back right here, and we can get the velocity function. Okay. So the C here is as V naught, right? Initial velocity. Okay. Now we're going to integrate this one more time, and we try to get the vector function, right? So integrate this one more time, what do we get?
Negative GT squared over 2.
Yes, and in J direction plus
Yeah.
V naught what? T,
T,
right?
T.
Yeah, you got it, okay. Okay, and then plus another constant vector, which is dy here, right? Okay, don't forget, every time when you take anti-duality, you need the constant like that, right? Okay, now we're going to plug in t equal to 0, and we try to figure out the d. What does d equal to? Correspond to? R of what?
0.
R of 0. That's the initial position vector. So in this case, okay, in this case, what is the initial position vector?
0.
It's 0. Yeah. So in this case, d is equal to 0. So putting all this together, right? So we're gonna put the d equal to 0 here. We get the vector function for the projectile, right? So we got this. Does it look familiar to you guys in physics class? You remember that one? Negative gt squared plus t times the initial velocity. Okay. Maybe you will see that. If you haven't, then maybe see that in physics. Okay? That's good. Okay, let's call this equation 3. Okay. All right. Now let's continue. Okay. We figure out the vector function for the projectile, but we haven't figured out what angle here will maximize the span, right? Okay, let's figure this out. Okay. So if we write this, the magnitude of V naught as V naught, or we just put V naught there. Okay. The magnitude of that is just V naught. Okay. The book actually has this one here ball face, but this one here is not ball face. Okay, so this is a vector, but this is not a vector. Okay, so think about that as just the initial speed of the projectile. Okay, that's this one. Okay, then if you decompose this initial velocity into the I and J direction, okay, then you can get. Okay, so how do you get that? So if you decompose that into this I direction, basically it just takes this times cosine alpha, right? Okay, this times cosine alpha will be the speed in the x direction. Okay, so this is the one. And then this V naught times sine alpha, then you get the opposite of this angle. That's the velocity in here. Now that's the speed. Okay, that's the speed on the y direction right there. Okay, so you can actually decompose this velocity in the x and y direction this way. Okay, this is this, and this is the x direction, this is the y direction. Okay, so the equation 3 above, and it become this vector function. So with the x component function to be this, okay, and then the j component will be this. Well, where does this one come from? We just substitute v naught to be that. Okay, remember we pick this one, right? This one here only has the j component. Okay, so that's why the j component will have this, but the I component will have the same as the V naught, like this. Okay. So just substitute V naught into equation 3, you got this. Okay. So the parametric equation of the trajectory are therefore x equal to what? X equal to this part right here, right? This is the x component, right? And then the y component will be what? This one over here, right? Okay. So those are the parametric equation of the trajectory. We try to we trying to maximize the x, right? Right there. But when you hit, okay, what happened here when you hit? When you hit the ground right here, y is equal to 0, right? Y equal to 0. So we can try to figure out the time. So using that y equal to 0, we can figure out what time it's going to hit the ground right there, right? So we're going to set y equal to 0. So we're going to set y equal to 0 in the second, in this, okay? Set y equal to 0 in here. So you get 0 over here, and then you try to solve for t, okay? So what do you get? Set y equal to 0, solve for t. You can take out a common factor t, right? And factor that. So you get t equal to 0 or t equal to what? Can you work this out? Or t equal to 2 v naught sine alpha divided by g. Yes, you got it. Okay. So you got that one. Okay. So we got 2 times. This one corresponds to when you first throw the ball, right? It's still on the ground, the ball, right? And then this one here is when it landed on the ground after you throw the ball. Okay, landed there. Okay. This second value of t then give the span, right? The distance. Okay. So that's equal to the x coordinate at that time. So how do you find that? Well, you can just substitute t equal to this into this one, right? T equal to that into this one. You can try to figure out this x, okay? To find the x coordinate at that time, okay? So over here, I just substitute t over here, and put it into the parametric equation for the x component. Then we got this. Okay, we got that. And we'll just do some rearranging. So we put the 2 sine alpha cosine alpha here, and we use the double angle formula. Okay, what's the double angle formula? Sin 2 theta equal to 2 sin theta times cosine theta, right? Okay. All right. And then we got this one over here. Now looking at this, right? So remember the initial velocity is fixed already, right? This is the gravitational acceleration is fixed. Those are constant. So if we can maximize this, then the x here will be maximized. The span here will be maximized. What alpha gives you the maximum sine to alpha? What does alpha equal to? How big can sine be? What's the maximum for sine? 1, right? So how can I get this to be 1? When you throw the angle, it's an RQ angle, right? Pi over 2. Alpha, I'm talking about. So sine of power 2 is 1, right? So 2 alpha will be equal to power 2. So alpha equal to power 4. In other words, in degree, it is 45 degrees, right? Okay. So that's 45 degrees. So next time when you try to throw a ball, try to end it so then the angle is 45 degrees. It's gonna reach the maximum span. Okay, the furthest. Okay. I guess I don't know if every football player knows that, but anyway. Okay, if you neglect the resistance, air resistance. Okay. Does it make sense to you guys? Okay. Okay, I'm gonna let you guys practice on this. This problem over here. How about you guys work in a group so you can figure this out?